Satellite-scale wildlife monitoring, science that changes conservation. What makes satellite-scale wildlife monitoring truly revolutionary is that it transforms conservation from observation into prediction. For the first time in human history, ecosystems are no longer studied only after change happens. They are modeled while change is happening. Satellites capture the pulse of forests, grasslands, oceans, and deserts continuously. Every pixel becomes a data point. Every data point feeds algorithms that learn how life behaves at planetary scale. At the core of this system is orbital mechanics. Earth observation satellites typically fly in low Earth orbit, between 400 and 800 kilometers above the surface. At this altitude, they complete one full revolution around Earth every 90 to 100 minutes. That means the same satellite can pass over the same location multiple times per day. Constellations of satellites, sometimes hundreds working together, create near-continuous coverage of the planet. Each satellite carries specialized instruments. Optical sensors collect visible light reflected from Earth. Infrared sensors measure heat radiation. Microwave radar penetrates clouds and vegetation. Hyperspectral imagers break sunlight into hundreds of narrow wavelength bands, revealing chemical composition invisible to human eyes. Together, these instruments transform Earth into a living laboratory. Animals interact with this system through physics. Every warm-blooded animal emits thermal radiation. A large mammal typically radiates energy at temperatures around 30 to 40 degrees Celsius, producing infrared signatures distinct from surrounding terrain. Thermal satellites detect this contrast even at night. When groups of animals gather, their combined heat creates measurable clusters in thermal imagery. Artificial intelligence systems identify these clusters, estimate population density, and track movement across landscapes. But heat is only one signal. Movement itself becomes data. When animals migrate, they alter vegetation patterns. Grazing reduces plant reflectance. Trampling changes soil structure. Paths form across grasslands and forests. Radar satellites detect these changes through variations in surface roughness and backscatter intensity. Over time, machine learning models recognize these patterns as biological activity. This allows scientists to map wildlife corridors without ever seeing the animals directly. Vegetation health plays a central role. Satellites measure photosynthesis using the normalized difference vegetation index, calculated from reflected red and near-infrared light. Healthy plants absorb red light and reflect infrared. As vegetation grows, NDVI values rise. As drought or disease spreads, NDVI falls. Animals follow vegetation. By correlating NDVI trends with historical movement data, AI predicts where herds will travel weeks or even months in advance. Migration becomes a mathematical outcome of plant physiology and rainfall physics. Water availability adds another layer. Microwave satellites measure soil moisture by detecting changes in dielectric properties of the ground. Wet soil reflects radar differently than dry soil. These measurements reveal hidden water reserves, drying riverbeds, and emerging wetlands. Wildlife responds to these changes long before humans notice them. AI integrates this information to forecast gathering zones during dry seasons and dispersal patterns during floods. Temperature gradients matter too. Surface temperature influences insect populations, breeding cycles, and metabolic rates. Thermal satellites capture land surface temperatures with resolutions down to tens of meters. AI models combine temperature maps with species-specific tolerance ranges to identify habitable zones and climate stress boundaries. This is physiology merged with orbital physics, but satellite wildlife monitoring goes far beyond tracking animals. It models entire ecosystems as dynamic systems governed by energy flow. Solar radiation enters Earth's atmosphere at roughly 1,361 watts per square meter. Plants convert a small fraction of this energy into chemical bonds through photosynthesis. Herbivores consume plants. Predators consume herbivores. Decomposers recycle nutrients. Heat dissipates back into space. Satellites measure every stage of this process. They track carbon uptake in forests. They detect methane emissions from wetlands. They monitor phytoplankton blooms in oceans by measuring chlorophyll concentration. They observe desert expansion and ice sheet retreat. Wildlife becomes part of a planetary energy equation. Artificial intelligence processes this information using deep neural networks trained on decades of environmental data. These systems learn how ecosystems respond to temperature shifts, rainfall variability, and human activity. They simulate future scenarios by solving coupled differential equations representing atmosphere, biosphere, and hydrosphere interactions. This creates digital twins of Earth. Digital twins are virtual replicas of real ecosystems. Scientists can simulate droughts, heat waves, deforestation, and conservation strategies inside these models before applying them in the real world. They can ask, what happens if rainfall drops by 10%? What if temperature rises by 2 degrees Celsius? What if migration corridors are blocked? The model answers. By 2026, these systems achieve predictive accuracies of above 80% for many ecological outcomes. That means conservation decisions are no longer guesses. They are forecasts. One of the most powerful outcomes of this technology is early warning detection. Satellites identify subtle changes in vegetation reflectance that signal stress weeks before plants visibly die. Thermal sensors detect abnormal heat patterns that indicate disease outbreaks in animal populations. Radar reveals illegal deforestation before trees are fully removed. AI flags anomalies automatically. Human teams receive alerts. Intervention happens earlier. This shifts conservation from reaction to prevention. Satellite-scale monitoring also reshapes how biodiversity is measured. Traditional surveys counted animals in small regions. Now AI estimates population size across entire continents. Spatial statistics models analyze clustering behavior. Entropy metrics quantify ecosystem diversity. Graph theory reveals social networks within animal groups. Even vocalizations become data. Orbiting acoustic sensors combined with ground microphones capture animal calls. AI classifies species by sound. Migration timing is inferred from seasonal changes in acoustic landscapes. The wild becomes measurable. Meanwhile, GPS collars weighing less than 50 grams transmit real-time location and physiological data from animals. Heart rate variability indicates stress. Accelerometers reveal activity patterns. When combined with satellite imagery, scientists correlate behavior with environmental conditions. This reveals how animals experience climate change directly. Future systems will go even further. Hyperspectral satellites already detect subtle chemical differences in vegetation that indicate nutrient deficiency or disease. Upcoming quantum gravimeters may map underground water reserves by measuring tiny variations in gravitational fields. Photonic processors on board satellites will analyze data using light, reducing processing time from minutes to microseconds. Edge AI will soon operate directly in orbit, filtering imagery before it reaches Earth. This reduces latency and allows near-instant ecological alerts. Soon, satellites may detect animal health from space by analyzing thermal patterns and movement irregularities. The planet becomes biologically observable. What's emerging is not just monitoring, it's planetary intelligence. Earth is becoming a self-measuring system, but perhaps the most profound impact is philosophical. For the first time, humanity can observe nearly every ecosystem continuously. Borders disappear. Remote regions become visible. Patterns emerge that were invisible for millennia. We see migration routes spanning countries. We see forests breathing through infrared. We see oceans bloom with microscopic life. We see deserts expand. We see ice retreat. We see extinction approaching. And we see recovery possible. Satellite wildlife monitoring reveals that Earth is not a collection of isolated habitats. It is a single interconnected system. Physics connects everything. Photons drive plants. Plants feed animals. Animals shape landscapes. Landscapes influence climate. Climate reshapes life. Satellites measure the loop. Artificial intelligence interprets it. Humans finally understand it. By 2026, conservation is no longer limited by distance or scale. It operates at planetary resolution. It uses mathematics instead of guesswork. It predicts instead of reacts. It protects before collapse. And this technology is not about control. It's about awareness. Because when you can see ecosystems from space, you realize how fragile they are. When you watch herds migrate across continents, you understand how connected life is. When AI models predict biodiversity loss decades ahead, you realize responsibility comes with knowledge. Satellite-scale wildlife monitoring doesn't just change conservation, it changes perspective. It teaches humanity that we are not separate from Earth. We are inside its equations, and this is only the beginning. Next, we will explore how AI predicts ecosystem collapse before it happens, how quantum sensors may reveal underground life networks, and how future satellites could monitor every species on Earth in real time. So stay with this series, because the wild is no longer hidden. It is becoming visible, from orbit, from algorithms, from science, and from us.